Multimodal AI refers to systems that can process, understand, and generate information across more than one type of data modality. A modality is simply a form of data representation, such as text, images, audio, video, sensor signals, or structured data. Traditional AI systems were typically unimodal. A vision model classified images. A speech recognition model transcribed audio. A language model processed text. Multimodal systems attempt to unify these capabilities so that information from different modalities can be combined, aligned, and reasoned over in a coherent way. To understand why multimodality matters, consider how humans interact with the world. We rarely rely on a single modality in isolation. When someone speaks to us, we process their words, tone of voice, facial expressions, gestures, and the surrounding visual context. Our understanding emerges from integrating these signals. Multimodal AI aims to replicate aspects of this integrative capability in computational systems. At an architectural level, multimodal systems typically consist of modality-specific encoders that transform raw inputs into a shared representation space. For example, an image encoder might convert pixel arrays into high-dimensional feature vectors. A text encoder might transform token sequences into contextual embeddings. An audio encoder might process waveforms into spectrogram-based features, and then into embeddings. These embeddings are then aligned or fused in a shared space where cross-modal interactions can occur. One common design pattern is the dual encoder architecture. In this setup, each modality has its own neural network encoder. The encoders are trained so that semantically related inputs from different modalities produce embeddings that are close to each other in the shared space. For instance, an image of a cat and the text description a small domestic feline would produce embeddings that are similar. Training objectives encourage this alignment by rewarding the model when matching pairs are closer than mismatched pairs. Another design pattern is the use of a single transformer architecture that processes tokens from multiple modalities. In such systems, images, text, and sometimes audio are converted into token-like representations and fed into a unified transformer. The model learns to attend across modalities using self-attention mechanisms. This allows the system to reason jointly over text and image regions, for example, answering questions about an image by attending to both the question tokens and relevant visual tokens. An important technical challenge in multimodal AI is representation alignment. Different modalities have very different statistical properties. Images are high-dimensional continuous signals with strong spatial structure. Text is discrete and sequential. Audio is continuous and temporal. To align them, models must learn embeddings that capture semantic meaning rather than modality-specific noise. Large-scale paired datasets are often used, such as image caption datasets or video text datasets. Diversity and quality of these datasets significantly influence the system's ability to generalize. Multimodal applications span a wide range of domains. In image captioning, a model generates textual descriptions of images. This requires visual understanding and language generation. The visual encoder extracts features from the image, and a language decoder generates a description conditioned on those features. Attention mechanisms often help the model focus on specific regions of the image while generating corresponding words. In visual question answering, the model receives an image and a natural language question about that image. It must integrate visual features and linguistic information to produce an answer. This task requires not only object recognition but also relational reasoning. For example, answering a question like "What is the person holding?" requires identifying the person, detecting objects in their hands, and mapping that to a textual answer. Another major application is speech-enabled conversational agents. These systems integrate speech recognition, natural language understanding, dialogue management, and speech synthesis. The audio signal is first converted into text through an automatic speech recognition model. The text is then processed by a language model to generate a response. Finally, the response text is converted back into speech using a text-to-speech system. While this can be implemented as a pipeline of unimodal models, increasingly there are attempts to build end-to-end systems that jointly optimize across these modalities. In the domain of autonomous systems, multimodal AI is critical. Self-driving vehicles rely on cameras, radar, LiDAR, and sometimes ultrasonic sensors. Each sensor modality provides different information. Cameras capture rich visual detail but may struggle in poor lighting. Radar can detect object distances and velocities but with less detail. LiDAR provides accurate depth measurements. A multimodal fusion system combines these signals to produce a coherent representation of the environment. The fusion can occur at early stages, where raw sensor data is combined, or at later stages, where high-level features or decisions are merged. Medical AI is another area where multimodal approaches are valuable. A diagnostic system might combine radiology images, electronic health records, laboratory test results, and physician notes. Each modality contributes complementary information. Integrating them can improve predictive accuracy and robustness. However, medical data often comes with privacy constraints and limited availability, making training large multimodal models challenging. Multimodal generative models have gained particular attention. These models can generate images from text descriptions, generate text descriptions from images, or even generate video from textual prompts. The architecture often involves conditioning one modality on representations derived from another. Diffusion-based models, autoregressive transformers, and hybrid architectures have all been used for such tasks. The key principle is that the model learns a joint distribution over multiple modalities, enabling it to sample one modality conditioned on another. An important concept in multimodal systems is cross-modal attention. In a transformer framework, attention allows tokens to weigh the importance of other tokens. In a multimodal setting, text tokens can attend to image tokens and vice versa. This creates a mechanism for dynamic interaction. For example, when generating a word in a caption, the model may attend strongly to specific image regions that are relevant to that word. This selective focus improves interpretability and performance. Training multimodal models at scale often requires vast computational resources. The number of parameters can be very large, and the datasets may contain millions or billions of paired examples. Efficient training strategies, distributed computation, and memory optimization are essential. Additionally, balancing modalities during training is non-trivial. If one modality dominates the training signal, the model may underutilize the others. Evaluation of multimodal systems presents unique challenges. Traditional metrics for text or image tasks may not fully capture cross-modal understanding. For image captioning, automated metrics compare generated captions to reference captions, but they may not reflect true semantic correctness. Human evaluation is often necessary. For tasks like visual question answering, accuracy on benchmark datasets provides some indication of performance, but models can exploit dataset biases rather than truly understanding visual content. Bias and fairness issues are amplified in multimodal systems. If training data contains stereotypical associations between certain visual features and textual descriptions, the model may reproduce these biases. For example, it might associate certain professions with specific genders based on biased data. Addressing these issues requires careful dataset curation, bias detection techniques, and alignment strategies. Robustness is another concern. Multimodal systems may be vulnerable to adversarial perturbations in one modality that influence the output in unintended ways. For instance, small changes to an image that are imperceptible to humans could alter a generated caption. Similarly, subtle changes in audio input might cause transcription errors that cascade into incorrect downstream responses. Designing models that are robust across modalities is an active area of research. From a systems integration perspective, deploying multimodal AI involves handling heterogeneous data pipelines. Images may require pre-processing such as resizing and normalization. Audio may require sampling rate adjustments and noise filtering. Text may require tokenization and normalization. Ensuring synchronization between modalities is crucial, especially in video and audio applications where temporal alignment matters. Another emerging direction is multimodal reasoning. Beyond simple alignment or generation, the goal is to perform higher-level reasoning that integrates evidence across modalities. For example, Analyzing a scientific diagram along with its accompanying text to answer complex questions requires understanding both the visual layout and the textual explanation. This pushes models toward more structured internal representations. Transfer learning plays a significant role in multimodal AI. Large pre-trained vision models and large pre-trained language models can be combined and fine-tuned for specific multimodal tasks. This reduces the need for massive task-specific datasets. However, aligning pre-trained components is not trivial. Differences in embedding spaces, scale, and training objectives must be reconciled. There is also growing interest in grounding language in perception. Purely text-based models may generate plausible but ungrounded statements. By incorporating visual or sensory grounding, models can tie language to real-world entities and events. This can improve factual consistency and reduce hallucination in some contexts. Grounding also enables applications such as robotics, where language instructions must be mapped to physical actions in a real environment. Human-computer interaction is being transformed by multimodal AI. Instead of typing commands, users can speak, gesture, or show images to communicate intent. Systems that understand multiple input modalities can provide more natural and intuitive interfaces. For example, a user might point to an object in an image and ask a question about it. The system must interpret both the pointing gesture and the verbal query. Privacy considerations become more complex in multimodal systems. Visual and audio data often contain personally identifiable information. Storing and processing such data raises ethical and regulatory concerns. Techniques such as on-device processing, federated learning, and differential privacy may be applied to mitigate risks. As multimodal models grow in capability, there is increasing discussion about their role as general-purpose AI systems. By integrating text, vision, and audio, these models can perform a wide variety of tasks within a single architecture. However, specialization still matters. Domain-specific multimodal systems often outperform general ones in targeted applications due to tailored training and constraints. In terms of architecture, future multimodal systems may move toward more unified representations where modality distinctions become less rigid. Instead of separate encoders, a single model may process tokenized representations of all modalities in a common format. Research is exploring ways to represent images, audio, and video as sequences of discrete tokens, enabling unified processing. Ultimately, multimodal AI applications reflect a broader shift from narrow task-specific models to integrated systems capable of perceiving and generating across diverse data types. The underlying working principles involve representation learning, alignment across modalities, attention-based interaction, large-scale pre-training, and careful fine-tuning. The architectural challenges include handling heterogeneous data, ensuring efficient training, maintaining robustness, and aligning outputs with human expectations. For a technical audience, the key takeaway is that multimodality is not just about adding more input channels. It is about designing architectures and training strategies that allow different forms of information to reinforce each other. It requires careful consideration of representation spaces, data alignment, computational efficiency, and evaluation methodologies. As these systems continue to evolve, they will increasingly shape how humans interact with intelligent machines, blending language, vision, and sound into cohesive, context-aware applications.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.